Hello and welcome to all students. In this lecture we study about the calculus third, unit number third. Name of the unit number third is applications. So first application is second order Taylor's formula for scalar field. So we know that the Taylor's theorem is useful for approximating a function near a given point by means of polynomial. If f is a real valued function differentiable n times at point A, then for small h, f of a plus h for small h, for small h, f of a plus h, f of a plus h can be approximated by polynomial in h using Taylor's theorem. Okay, we extend the theorem for scalar. We can extend the theorem for scalar field in two variables, and we approximate f of a plus f of x comma y near a point a1 comma a2 by means of polynomial of two variables. So we can write the formula for Taylor's formula for function of two variables. Our next application is Jacobian. Writing the Jacobian for a vector valued function. Okay. Second application is Jacobian matrix for a vector valued vector field or vector valued function. So first of all we write the definition. Let f from S to S, let S is a subset of Rn and f is a function from S to Rm, be a vector valued function given by f is equal to f of f1 comma f2 comma dot 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 fm. There are m vectors. Okay, function f is acting on a point with n coordinates, and we get a function when we get a point in Rm with m coordinates. Let a belongs to S, and dou fi by dou xi at a exists for I is equal to 1 to n, then means partial derivatives of all functions with respect to all variables exists. Then the Jacobian matrix of function f at the point A denoted by jf of a and is defined as the m cross n matrix written like this. So Jacobian matrix of function f at point A is equal to, first row is dou f1 by dou x1 at point A, dou f1 by dou x2 at point A, dot 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 dou f1 by dou xn at point A. Second row is dou f2 by dou x1 at point A, dou f2 by dou x2 at point A, dot 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 dou f2 by dou xn at point A, and final mth row is dou fm by dou x1 at point A, dou fm by dou x2 at point A, dot 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 dou fm by dou xn at point A. So this is the matrix of order m cross n. Okay, so based on this, let us try to solve some problems now. Okay, so let us write the example number 1. Find the Jacobian matrix. Find the Jacobian matrix of the following vector field. Following vector field, and the vector field is given F is a vector field from R2 to R3, and it is defined by f of x comma y is equal to 2x square plus 3y comma 4x minus 2y comma x cube plus y cube. Bracket complete. At -1 comma 1 full stop. Okay, so this is our vector valued function, and we find the Jacobian of this vector valued function at point -1 comma 1. So let us write the answer. For this question. Okay, so let given function f is equal to f of f1 comma f2 comma f3, where f1 is equal to function 2x square plus 3y, function f2 is equal to 4x minus 2y, and function f3 is equal to x cube plus y cube. Okay, and let us take a is equal to point -1 comma 1, and what we have to find Jacobian of function f at point A. Okay, so we write that Jacobian first of all. So here Jacobian of function f at point A is equal to Jacobian matrix is equal to matrix is equal to, so first row is dou f1 by dou x at point E, dou f1 by dou y at point E. Second row is dou f1 by dou x, dou f2, dou f2, okay, at point A, and dou f2 by dou y at point A. And third row is dou f3 by dou y, dou x at point A, and dou f3 by dou y at point A. So we have to find all these 6 derivatives. Okay, so let us try to find out all these 6 derivatives now. So first of all, we write derivative, partial derivative of function f1 with respect to x. It is equal to dou by dou x. F1 function is 2x square, as we have written above, 2x square plus 3y, and its partial derivative with respect to x is 4x. Okay, 4x, and the value of this partial derivative at point A is equal to, so point A is dou f1 by dou x at point A. Point is 1 comma minus 1, means x is 1, y is minus 1, so it is 4. So thus we have first value. Now let us go to find the second partial derivative of f1. So second is dou f1 by dou y, and it is equal to dou by dou y of the function 2x square plus 3y and it is equal to, it is 3. Therefore the partial derivative of function f1 with respect to y at point A is equal to 3. Okay, now let us go to next function f2, and find its derivative, partial derivative with respect to x. So dou by dou x of function f2 is 4x minus 2y, and its derivative with respect to x is 4, and therefore the partial derivative of f2 function with respect to x at point A is equal to 4 also. Okay, also 4. Now we find the partial derivative of f2 function with respect to y, okay, at point A, with respect to y first, then we will find at point A. Okay, and it is equal to dou by dou y of f2 function is 4x minus 2y, and it is equal to minus 2. Therefore for f2 function, partial derivative at point A with respect to y is minus 2. Okay, so these are the values, okay, which we need while writing the derivative. Now let us go to the next function, f3 function, and find its partial derivative of this partial derivative of f3 with respect to x. It is equal to dou by dou x of f3 is x cube plus y cube, and its partial with respect to x is 3x square. Now find dou f3 by dou x at point A, and it is equal to dou f3 by dou x, and at point A is 1 comma minus 1 and value is 3. So this is the next value that we will use. Now find the partial derivative of f3 function with respect to variable y, and it is equal to dou by dou y of the function f3. f3 is x cube plus y cube, and its partial with respect to y is 3y cube. Okay, and we find the value of this partial derivative at point A. It is equal to dou f3 by dou y at point 1 comma minus 1, and it is equal to, if I put y equal to minus 1 here, so let us here must be square, and if I write y equal to minus 1, so value will be 3 only. So in this way we uh, found all the values of partial derivative at point A, and now we are ready to write the Jacobian of function f at point A. So that Jacobian is equal to okay. So we have to write the matrix notation. Okay, so our first entry or first row is 4 3, second row is 4 minus 2, and third row is 3 3. Okay, so this is the required Jacobian matrix of a given function at point A. So similarly, let us go to the next question now. Let us go to the question number 2, or example second. Okay, here also given that f is a function from R4 to R2, it is a vector valued function, vector field defined by as, and it is defined like this: f of x comma y comma z comma w. Function f is acting on 4 point vector with four components, and we get a vector with 2 components. So first component is x square plus 2y, and second component is x plus z square plus 3 times w square. So this is the vector value function, and we have to find the Jacobian. Find Jacobian of f at point A, where point A is equal to 3 comma 1 comma 0 comma minus 1. Okay, so problem is very simple, not so very difficult, not so difficult. Okay, so let us go to write the answer of this question. Answer. Okay, write the answer of these questions. So let us write. So f is a function. Let f be the function f of f1 comma f2. Okay, where f1 is equal to x square plus 2x, x square plus 2y, and f2 function is equal to x plus z square plus 3 times w square, and point A is given, it is 3 1 0 minus 4. Okay, this is the point in R4. Now we start to find out. So first of all we write the formula for Jacobian. Okay, so what is the Jacobian for this function now? Okay, so here Jacobian of function f at point A is equal to, and it must be a matrix of order 2 by 4. Okay, 2 by 4. So we need to write a matrix of order 2 by 4. 2 rows, 4 columns. 2 rows, 1 minute. Okay, okay. So matrix notation. Two rows. So what is first row? First row is 4 columns. Okay, so dou f1 by dou x, dou f1 by dou y, dou f1 by dou z, and dou f1 by dou w. Second row is dou f2 by dou x, dou f2 by dou y, dou f2 by dou z, dou f2 by dou w. Okay, so this is a matrix of order 2 by 4. And all these partial derivatives we have to find at point A. Okay, so let us go, let us try to find now all these derivatives. Okay, so you will observe that first partial derivative here dou f1 by dou x is 2x and its value at point A. So this implies dou f1 by dou x at point A is equal to at point A is 6. Then we find dou f1 by dou y is equal to is 2, and this implies that value of f1 with at point dou f1 by dou y at point A is equal to 4. Then dou f1 f1 by dou z is equal to 0, and this gives dou f1 by dou z at point A is again 0. Then dou f1 with respect to dou f1 by dou w is equal to again 0, and it is equal to dou f1 by dou w at point A is value is again 0. Okay, so these are the derivatives in the first row. Now we find the derivatives in second row. Now we find dou f2 by dou x is equal to, it is 1, and this implies that dou f2 by dou x at point A is equal to 1. Now dou f2 by dou y is equal to 0, and its value at point A is equal to 0. Now let us go to the next derivative. Partial derivative of f2 with respect to z is equal to 2z, and its value at point A is equal to, just put z coordinate here, xyz z coordinate is 0, therefore value is 0. Now last is partial derivative of f2 with respect to w is equal to, with respect to w is 6w, okay, 6w, and we find the value of this partial derivative with at point A, and point E w coordinate is -1, so it is -6. Okay, so these are the values in second row. Now we can write the Jacobian of function f at point A. It is equal to, it is a matrix, okay, okay. Matrix of order 2 by 4. So first row is 6 4 0 0. Second row is 1 0 0 -6. Matrix of order 2 by 4. So this is the Jacobian of given function at a given point. So this is the end of our lecture. Okay, and thank you for paying attention.